Hello, my name's Alan Rose from Corrdesa, and today I'm going to talk about our mobile non-drip brush plating and anodizing technology for repairs. So the agenda is I'll introduce Corrdesa, a little bit about what we do. We'll look at hostile environments and why corrosion repair is necessary. And we'll look at the technology, the non-drip brush plating and anodizing technology, and the non-drip tooling design, where we use computer-aided simulation to help that design process. I have a few project examples then, and we'll wrap up with some conclusions. Okay, so Corrdesa, we're a small company in Georgia, Tyrone, Georgia. Where is that? It's not very far from Atlanta. In fact, it's only 25 minutes away from the airport, Atlanta Airport, Georgia. Folks that have contributed to this are my colleagues Keith Legg and Siva Polani. If anybody wants a PDF of this presentation, please reach out to me. And my background is essentially computational fluid dynamics, more recently modeling electrochemical processes. Keith's background, he's an expert in coatings and hazardous materials reduction, and Siva, he heads up our laboratory and our data acquisition capability when it comes to testing of materials and acquiring material data. So, as a company, Corrdesa, our mission is to help clients quickly develop, qualify, and implement corrosion-resistant materials and coatings and associated application processes, as well as the hardware to actually apply those coatings. And we're always cognizant of the regulatory requirements, such as REACH, that is reducing the options for some coatings, such as reduction of chromates, banning of cadmium. So we make a lot of use of computer simulation to speed up optimization of our repair processes and hardware design. Okay, so let's talk about environments. Very hostile environments in military, particularly for the Navy here. I always like to show this, where you can see gallons and gallons of salt water being dumped onto these assets. And we have an FA-18 here down at the bottom. In fact, if you were to open up the wing composite panel on that FA-18, this is the kind of this is what you'd find, all this corrosion here. And all of these holes have to be redimensioned, maybe with the use of bushings. That's a common repair method. In fact, it's very important because more than 80% of military aircraft structural failures initiate corrosion pits. So, maybe some of these bushings or areas might need plating, or the aluminum structure need anodizing. So having a tool that can be mobile and brought in to do these repairs would be of great advantage. Okay, so let's talk about selective plating or brush plating. I have a couple of movies here. On the left hand side at the bottom, you see a traditional brush plating. We have an electrode, we have a workpiece, and the electrolyte is flowing through here. It has to be captured. The waste has to be captured in this tray. There's also a ventilation here, local ventilation, and you connect a rectifier to these so you can plate the piece. Now we'll talk a little bit more detail here about the non-drip plating technology, the ballistic, where we can actually plate a component without any drips. So if you can do that, you can reach very awkward places in an airplane here, and avoid having to set up all this masking and ways of capturing excess electrolyte on this FA-18, for example. Indeed, when we look at this guy here and zoom in, this is a tin zinc process where the plating around this avionics compartment. It takes a lot of time to set up all these polythene chutes and masking, so you can save a lot of time there with a non-drip method. So how does the tool actually work? So it's a closed loop electrolyte system. So if we zoomed in on the tool there is actually a porous media that is inserted into here, and we supply electrolyte to this porous media with one pump, and we suck back electrolyte and the excess electrolyte and ambient air through the other circuit with another pump, and then we connect the tool to the workpiece via a rectifier, so we can actually electroplate. You can also anodize as well. It's just reversing the current and using the appropriate electrolyte. So if I go here, you can see in this close-up of the tool a platinized titanium anode. You can see these injection points here where the electrolyte comes in and soaks that porous media, and then this annulus here sucks back that excess electrolyte. Now then, where we're adding to this technology at Corrdesa, we're working with Dalek, and we've developed a workflow. We do a lot of computational aided engineering in our engineering work. We use simulations to design and optimize various hardware and processes, and what we can do using computational fluid dynamics and using the Delistic tool as validation, we can predict what conditions it will drip and at what conditions over here on the right in which you would just soak the pad enough, because too much electrolyte and it will drip if the pumping rate is too high. If you don't supply it enough of a rate, then it will be the porous media will be dry and starved, and it won't plate or anodize. Similarly, the rate at which you suck back that electrolyte has to be just in balance. You have to get that sweet spot, and we can predict that for any kind of tool in geometry now, so we can scale up and design new and custom tools for different repairs. So that's really extended the capability of this technology. So we were working on that FA18, looking at that tin zinc plating problem, and something else came along. They had an issue in the Navy here with the P8 of Poseidon, and there are many areas on this plane where there's aluminum, and it's corroding far sooner than they expected. So they had also lightning strike damage on this port here, this static port, but there's corrosion on the nacelles and the leading edges. So they were looking at a repair method that could prevent this corrosion. So we thought about the non-drip anodized process. So we actually optimized the process and we demoed on a real plane. It was just a matter of masking up the area to be anodized with just some physical abrading, and then we could actually anodize the port itself. This is to capture excess drippage. They didn't believe us at first that we could actually do this, but as a precaution, but it was actually a non-drip process. So it's straightforward really. Once you've got connected up, you just move the tool in this circular fashion, just like the old days. As a child, you might be using coloring in a coloring book. So that was great. That was successful. We redesigned the tool twice the size, and it did the process in half the time. And we used CFD to do that. Another activity on the plating side, we designed a custom system for F-35, for Lockheed F-35. This is ground support equipment, and they purchased 50 of these units, and they hope to get another 140. So this is a completely contained system. We have our rectifier, we have our pumps. This is for zinc nickel, a replacement of cadmium, electroplating, repairs on landing gear. And this is all done outside of the shadow of the aircraft. We have now these tools connected to 20 foot of tubing, protected by spiral guard, so you could run a car over this and it would still be okay. We also have tie downs here because this equipment can go on aircraft carriers, has to withstand, the brakes have to be strong enough for a slope because of that. So this equipment, it can also be completely enclosed, so it's like a Faraday cage to reduce any stray signals and such. The rectifier has arc suppression, so obviously you don't want sparks in areas where you may have volatiles from fuel. Now we've moved on to a couple of different projects where we're scaling up this capability for much larger repairs. There's a need to repair the floor of the cargo plane, the C-5 at the US Air Force. They have a standard repair here where they put a patch on this anodized floor when the floor has been damaged, but the anodize is also damaged. So we need a way of re-anodizing the floor here. This is very large aircraft. It can actually hold a couple of tanks indeed, and also the total length of this was longer than the very first flight that the Wright brothers actually made. Another thing as well is you could also play tennis if you got a little bit bored. Okay, so we had to actually do another test to show that this wouldn't drip because there's lots of features in the C-5 floor with these fasteners and kind of recesses with these handles on. So we did a very quick test where we put some absorbent material underneath here, and we did the anodizing. You can see tiny little kind of drips there that are there for a moment and then they're sucked back by the tool, but nothing actually comes through these holes. We also looked at the actual repair method itself. There's different ways of applying that anodize. There's one where we thought, well, first you need to do your masking and anodize, and then we thought we looked at another method where we actually introduced an overlap, which made a much more robust repair. Where you can see here we do our tape. Here we strip, we anodize, and then pull the tape off and then reset the tape back a bit and then re-anodize, and we've got a much better quality of finish at the end. So we'll look at all the different aspects of these processes. There's also another project that's just kicked off this last year where there's an interest in tackling the corrosion on fasteners or wing fasteners. They can't be taken out, they have to be tackled in situ. So we have a way of taking off the corrosion, removing the cadmium and replating with zinc nickel, and then re-anodizing any area of the wing where it had been damaged. So here you can see the fasteners are on the top of the C-5 wing. It's huge airplane. So big you can actually play cricket on the wing if you care to. Where is it going now? We did do some work for a client. They were interested in the impact of friction stir welds, and we did a test where rather than use a chem film anodyne type finish on this friction stir weld, we did a brush anodize, put them out on the beach for 9 months, and here's the difference. So I see some opportunity in the future where non-drip brush anodizing could really help folks that have an interest in the quality of the friction stir welds on their systems. So conclusions. I introduced mobile non-drip plating and anodizing technology. It's a lot safer, it's very quick to set up, so you've got a shorter turnaround time in repair. We've also globally deployed a zinc nickel plating system for F-35, so we've taken these technologies right through to commercial equipment that's robust and is out there. And the technology I've shown through our computer-aided engineering capability, we can develop very quickly custom scaled up tooling. And now we're working on other projects of faster corrosion issues, actually removing the corrosion as well electrolytically. and then replating and then re-anodizing any damaged areas. There's a huge interest in this area. There's a lot of old platforms out there that can benefit from this. And generally, I find it quite surprising how few people, although they've heard of brush plating, they don't realize you can actually do brush anodizing. So I think that's useful to take that away. And then I just finished off with some work that we did on the protection of friction stir welds, and it had a much bigger impact than just a chemical film protection. Okay, so Alan Rose from Corrdesa. Here's my contact details. If you have any questions, please feel free to reach out to me.